Hello, dear friends. This is the introductory lecture on the course Econometrics II. And in this lecture, we will cover the most important concepts from statistics and econometrics that provide the fundamentals to understand the material in this particular course. So I will skip slides on the organization of this course. We discussed them during our offline class. And let's start with the most important idea. The fundamental concept of econometrics is the idea of linear regression model. We start with a simple linear regression model, and the idea is the following. We have two variables, one variable y, we call this dependent variable, and another variable x, which is an explanatory variable. And we try to estimate their relationship or the effect of x on y using observations, using data, and these observations are denoted from 1 to n. So here is the formal expression to define this relationship. We have a linear part here, y equals beta 0 plus beta 1 times x1. This is the familiar expression for a line, plus ui. So we call x independent variable or regressor. We call y dependent variable. Beta 0 is called intercept. Beta 1 is called slope because it defines the angle of a line when we want to draw this relationship graphically. And ui is an error term. So what is an error term and what is the meaning of this error term? In real practice, and in the next slide you will see the example, in real practice there are almost no such relations where only one variable affects another variable. There are many more factors that can affect this outcome or dependent variable. And all those factors are included into this term u. So the error term consists of omitted factors or possibly measurement error in the measurement of y. In general, these omitted factors are other factors other than variable x that influence y. And this part of the expression, so the conditional expectation of y given x, which means that if I know x, I can calculate the expected value of y. What is the expected value of y? I refer you to the course of statistics, so you can watch it there. So the expectation is, let's say, the central value of a distribution of y. So in the distribution of y, something like an average or mean or expected value of y, if I know x, is described with this expression. And this part is called a population regression line. So I expect y to be this number if I know x. So throughout this lecture, we will have one empirical example. And this empirical example considers an effect of class size on test scores. So we want to investigate how does the class size affects an educational output in schools. So we start with this simple model of a linear relationship between a standardized 5th grade average test score and the student-teacher ratio. So we denote variable x. Now instead of x we have str. Instead of y we have this test score. And this is the initial population linear model. So now let's think about what is inside the error term. So of course, the class size is not the only factor that affects test scores in a district. Of course, it might be a teacher quality. It might be student economic background, family income, whether family is able to achieve some additional classes. Maybe these students have an access to some extra classes, extra groups, maybe some tutors who help these students to improve their test scores. It's not here, it's not in the class size. So luck, of course, you may be just lucky, and that's why you have a high value of a test score. Mistakes in gradient test. So test score might be somehow mistakenly calculated just by chance, because if it's graded manually, so maybe there are some mistakes. So, and the most important thing is the interpretation of regression coefficient. What is this beta 1? So formal or mathematical explanation is such that beta 1 is a partial derivative of a test score with respect to the student-teacher ratio. This describes that a change in student-teacher ratio by one student induces a change in test score by beta 1 points. So if I change number of students per one teacher, let's say by one student, by how much my test score would change by beta 1. And we want to know what is this beta 1 if you want to know how the class size influences the outcome of a group, educational outcome. So that was an idea of a linear regression. So now we move to the next part. What is the difference between population and sample? So first of all, the population regression line. We spoke about it. What is that? This is just a part beta 0 plus beta 1x. We have this line here, a blue line, and all these points around this blue line are exact pairs of x1 and y1, student-teacher ratio and a test score. And you see that these points do not belong to the line. And this distance from each point to the line is exactly u1. So I expect if a student-teacher ratio is 15, for example, I expect that the most likely test score is something like 660. But in this particular district, in district number 1, students have higher test score, 680. Why? Because there are other factors besides the student-teacher ratio that affected the test score. So probably they have less strict teachers. Probably in that district, students are richer, and that is why their parents can afford some additional classes. Maybe something else affected this higher outcome. We have another observation here for a bit higher student-teacher ratio. We expect the test score to be, well, let's say 655, somewhere here. But in this particular district, the real outcome is much lower, 640. Why is it so? Because, again, other factors other than student-teacher ratio affected this outcome, and this describes U error term for this second observation, and so on. So you will never observe such data where all lines, well, all points, all observations belong to only one line. There are always some other factors. So now, if you want to work with the linear relationship, we need to understand what is the probability framework of this linear regression. And this is the repetition of first part yes, actually of the whole idea of mathematical statistics course. So first of all, what is the population? Population of interest is a collection of all objects of interest. In our particular example, all school districts. So next, random variables, y and x. In our particular example, test score and student-teacher ratio. So why are these variables random? Do you believe that the test score is random? Of course, no. Test score is influenced by something for each student, for each school. The average test score is influenced by many factors. Why do we call these variables random? Because if we randomly select any school district, we cannot predict with certainty how much is going to be this value. This is the most important thing to understand. They are not random in a sense that they are randomly occurred, but they are random in a sense that when we collect the data, we do not know what the outcome of each district before we ask them, before we collect this data. The same story, for example, if I randomly call some telephone number, I don't know who is there. I don't know gender, I don't know age, I don't know weight of this person, I don't know the color of the person's eyes, nothing. I know nothing if I randomly call some telephone number. Before I do this and before I ask a person all these questions, for me, each variable is random. Gender, random. Weight, random. Age, random. I don't know. After I have this information, they are no more random. So then, joint distribution of y and x. We believe, this is our assumption, that there is a linear relation in the population between x and y. We believe that this population regression line holds, and this is the true relationship between these two variables. So this relation is called the population linear regression. So we already discussed it. Then the population objects or parameters beta 0 and beta 1 are unknown. We don't know them in advance. And if we want to tell something about these unknown parameters, beta 0 and beta 1, we need to collect, or we must collect, the relevant data. The relevant data on these variables x and y, on student-teacher ratio and test score. And the procedure that allows us to treat these variables as random, this procedure is called a simple random sampling. We need to choose n districts, n entities at random from the population of interest. So we have a lot of school districts, and among them we need to randomly select n 100, 200, 300, 400, 500 school districts randomly. And we need to observe x and y for each entity. We need to have the outcomes of these random variables. So simple random sampling implies that these pairs of x and y for each observation from 1 to n are independently and identically distributed, which means that their distribution is, first of all, independent of each other. So when I collect data on the second district, I cannot predict its outcome based on the outcome of the first district. They are independent of each other. So more on this concept of independency you may find in the mathematical statistics course. So identically distributed means that the distribution of each pair of each x and y is the same. Something like I expect each step, each observation, I expect the same outcome, and their distribution is identical. So for our example, as we already said, the population is all school districts on a country, random variables, test score and student-teacher ratio. Joint distribution is such that test score linearly depends on average student-teacher ratio in district. We do not know the effect of student-teacher ratio on a test score, beta 1. We don't know beta 0 as well. We need to randomly select n school districts and collect observations on their test scores and student-teacher ratio. And these two variables are independently and identically distributed. As I said, if we know test score and student-teacher ratio for one district, we cannot predict them for the other district. So now, how can we find the value of beta 1? So we would like to know the population value of beta 1. And we do not know beta 1. Nobody would tell us what is beta 1, what is the slope of a linear relationship between student-teacher ratio and a test score. We must estimate this using data. Now we collected n observations. With the help of these observations, we must estimate this beta 1. So we estimate these unknown parameters with the help of ordinary least squares estimator. So this is basically the special type of estimators, and the estimator is a rule that allows us, based on the data, to infer something about unknown parameters. So we denote estimators with this hat above each letter. So whenever beta 0 and beta 1 are population parameters, their OLS estimators are random variables, and we denote them with beta 0 hat and beta 1 hat. So this is important. Beta 0 hat and beta 1 hat, these estimators are random variables. So later we will discuss why they are random. And with the help of these estimators, we obtain a sample regression line, and the sample regression line looks similarly to the population regression line, but the difference is here you have estimators, beta 0 hat, beta 1 hat, both are random variables, and here instead of y, expected value of y, here you have y hat, which is called a fitted value or predicted value. So more on the estimation, more on the meaning of estimators you can find in mathematical statistics lecture and in Econometrics I topic intro to linear regression. So now let's compare the concepts of in population and sample. What are similarities? What are the differences? So in the population, we have all objects of interest, so all school districts. In a sample, we have a random sample of size m. We randomly select several objects from the population, and we have this n observations. So in the population, we have population parameters, beta 0 and beta 1, and those are constants. Those are some numbers, like 3, 5, 100, whatever. Those are numbers. In a sample, we have beta 0 hat and beta 1 hat, which are random variables, and their sample estimates just give us a particular outcome of those random variables. As you probably remember from statistics, random variables can take many possible values and they have some distributions, and we need to describe those distributions. So since we randomly selected n observations from a sample, sample estimates are also random. That's why. So in the population, all factors are hidden inside the error term, and in a sample, we have again another random variable which is denoted as u hat, and we call this residual. So a residual is an estimator of an error term. And regarding the regression line, in the population we have expectation, conditional expectation of y given x, which is beta 0, some number, plus beta 1, another number, multiplied by xi. In a sample we have two random variables, beta 0 hat and beta 1 hat, multiplied by x, and the result is fitted value of y hat. So now, why do we want to use these regression estimates, and how should we use the regression estimates? So here we can see the regression output from Python. We estimated that simple regression of test score on the student-teacher ratio, and we have these coefficient estimates. This is beta 0 hat, 698.93. This is beta 1 hat, minus 2, 2798. So the estimated or sample regression line has the following form. It's a test score hat equals 698.9 rounded minus 228 times student-teacher ratio. This is the estimated sample regression line. And you see that this line has a negative slope, which suggests that if a student-teacher ratio increases, so you have more students per one teacher, and it is logical that the teacher can pay less attention to each student, so the educational outcome decreases, right? So the more students per one teacher you have, the less is going to be a test score. So now going to the interpretation of these OLS estimates. So if you take a derivative of an outcome test score with respect to the student-teacher ratio, we will get this. So this is just a coefficient beta 1 hat minus 228. So what does this mean? So districts with one more student per teacher on average have test scores that are 228 points lower. If you have two more students per teacher, you need to multiply 228 by 2. That's gonna be 456 points lower. If you have three more students per teacher, well, you multiply 228 by 3 and you have some other number there. So this is the simple interpretation of this beta 1 estimate. So the intercept has slightly confusing meaning. If I put 0 here on a place of student-teacher ratio, I will get exactly the intercept for a test score, which means that districts with 0 students per teacher would have an average or predicted test score of 698.9. But this is something which makes no sense, because we cannot have in practice such a situation when we have 0 students per one teacher. Going back to the data here, you see that all our observations are somehow bounded between 10, 11, 12, 13, let's say 13 students per teacher and 27 students per teacher. So we don't know what is the educational outcome, what is the test score if student-teacher ratio is less than 10, because we don't have any observation on that. So this relationship is only relevant for the observed range from 13 students-teacher ratio to 27 students per teacher. Once again, the interpretation of an intercept, the straightforward interpretation, makes no sense because we do not observe this in data. So now, going to the fitted values. What are the fitted values? If you have an estimated regression line, y hat equals beta 0 hat plus beta 1 hat x, we are able to make predictions about y given values of x. So for our expression, if we have the first observation from the data, here we have the first line, and for the first district here we have a student-teacher ratio 17.89, let's say, and here we have the observed value of a test score. So observed values are here. But if the test score would depend only on a student-teacher ratio, then we would expect this value, 658.11. So once again, we observe this value of a test score in a district, and this 658.11 is the predicted value. So if a test score would depend only on student-teacher ratio, then we would have this value. So what does this mean? Remember that picture with the explanation of an error term. Now we can say, well, residual for this district, or kind of the difference between observed value and the predicted value, is 32.69. So this is unexplained part of a test score. We explained with the help of student-teacher ratio this part, and this part is explained by some other factors other than the class size. So now we need to outlay the probability framework for this estimation procedure in order to understand how we are able to infer about the coefficient estimates. So first of all, let's repeat once again that OLS regression line is an estimate. It is not a population regression line. We make the conclusions or inferences based on a limited random sample. And if we would have a different sample, we would get a different value of beta 1 hat. This is important to remember. The procedure of random sampling gives you the exact sample of n observations. If by chance you collect another sample with other observations, then you most probably have another value of beta 1 hat. What do we want to know? We want to know what is the uncertainty associated with this beta 1 hat. How far from each other would be these beta 1 hats if I collect different samples? If they're close to each other, or they're gonna be too far from each other. That's what I want to know. So another issue is to ask a question, given this beta 1 hat, how likely is this that beta 1, the true beta 1, is 0? Why do we want to know this? If true beta 1 is 0, and this is highly likely, then there is no effect of x on y. And we are proving something which does not exist. And the next, what we want to know is to construct a confidence interval for beta 1. So the interval that covers a true population parameter with a given level of confidence. So now, in order to describe the distribution of beta 1 hat, distribution of these estimators, we need to know several assumptions regarding the ordinary least squares. Those assumptions are very important, and in the course of Econometrics II, we deal with such situations when these assumptions do not hold, and how to overcome these situations when assumptions do not hold. So these assumptions are crucial to verify if your conclusions regarding the model are valid. So first and the most important assumption, that the conditional distribution of an error term given x has mean 0, or formally it's written here. So for each value of x, you expect that the error term is 0. This is a formal mathematical statement that other factors contained in the error term are unrelated to x. So basically, with the help of x, you cannot predict value of the error term. This is the crucial thing. And the illustration is shown here. So if you have a population regression line, beta 0 plus beta 1x, and now you have the value of student-teacher ratio 15. And as you remember about those points of data, so those points appear above or below the line. And the distribution of this error term around the line, or distribution of y when x is 15, is centered exactly at this line. So the expected error is 0. If this distribution is shifted upwards or downwards, then with the help of x, you can predict y better. You can capture the error term. Same here, once again, so the expectation of y is exactly at the regression line and the error term is 0. And here, for any particular value of x. But once again, try to remember the intuition behind this expression. So you should verify that other factors that influence y are not related to x. So we will see examples when it's true, when it's not true. So the second assumption, we already spoke about it. X and y and all these observations are independently and identically distributed. So basically we can ascertain this with the help of a random sample, with the help of simple random sampling from a single large population. If you establish this procedure before you collect the data, you are totally fine with that. So not IID examples. Values of x are set by a researcher as a part of experiment. So for example, you decide yourself which class would have student-teacher ratio 10, which class would have 15, which class would have 20. In this case, x and y for you are not random because you yourself decide which values of x are gonna be in each class or each district. So when observations refer to the same unit of observation over time, what does this mean? Think about the stock price. If you have today stock price, let's say $100, would you expect tomorrow this stock price to be 0 or 1 million? Probably no. Probably if you know the stock price today, which is 100, so tomorrow you will expect at least 100. This is your best guess for tomorrow. What does this mean? It means that it is not independent of another observation. So the value today influences the value of this variable tomorrow. And we will have this in the topic of panel data regression, because in the panel data regression we have observations across time, and those observations might be connected over time. So assumption number 3, something that you must not oversee in the data: large outliers are unlikely. So what are the outliers? Those are values of x and y, observations with values of x and y that lay far outside of the usual range. So here is an illustration. Look, we have many observations and most of them are on this regression line. And one observation is too far from the whole bulk of other observations, the whole range of other observations. And look what happens. If we throw away this outlier, then our OLS regression line would fit perfectly our observations. So the error terms are going to be very, very small. But if we use this observation, which is the outlier, then the OLS regression line would be shifted, and you see that it is not able to predict with the high degree of precision these values. So in this case, if you have an outlier, you just need to throw this away and work with the data that belongs to some reasonable range. So after these assumptions, and knowing these assumptions, we are able to establish something that is called the sampling distribution of a beta 1 hat. What is the sampling distribution? So first of all, we need to remember from the mathematical statistics that all estimators are functions of observable random variables. So once you collected the data, and once this data is the outcome of your random sampling procedure, you have an estimator beta 1 hat, which is some particular number. But in general, beta 1 hat is a random variable, and depending on your sample, it changes its value. So estimators are also random variables. And each random variable, according to the probability theory, has probability distribution. So regarding the estimators, we call this sampling distribution. So when we have a distribution of a random variable, we usually are interested in two values that are called moments. So the first moment is the expected value. So what is the expected value of beta 1 hat? And if this assumption holds, if the assumption of a conditional zero mean for the error term holds, then the expected value of beta 1 hat equals to the population parameter beta 1. And if this expression holds, beta 1 hat is called an unbiased estimator of beta 1. So if I can establish this conditional zero mean assumption, then my best guess for beta 1 hat is beta 1 itself, which is totally fine for me because it is what I want. I want that the most likely value of beta 1 hat based on the random sampling is going to be beta 1. Next step. For the random variable, I want to know what is the variance. So what is the variance of beta 1 hat, kind of sampling uncertainty? How far from this center I can receive values of beta 1 hat. And on the lecture in Econometrics 1, you may find the derivation of this formula. So basically this variance has very complex very complex look. And it depends on sigma squared I, and sigma squared to I is the variance of the error term. So this is important thing. It depends on the observations of X, and it depends on the error term. And looking at this formula, you can guess that if the variation in X is large enough, then denominator is going to be huge, because if the distribution of x's is very large, is very huge, so this sum is going to be also large. And then the variance of beta 1 hat is going to be small. So that's what you actually want. You want to collect a random sample such that x's, so the independent variables, have very wide range. So they actually kind of their values, their observed values, change from very small to very, very large numbers. And if the variance of an error term is huge, so if points of a data are distributed too far from each other, so basically the variation in y is huge, so then variation as beta 1 is also going to be large. So these are two opposite forces that drive the variance of beta 1 hat. So if you want to see the derivations of these formulas, go to the lecture Introduction to Linear Regression from the first part of Econometrics course. So now the sampling distribution of beta 1 hat and how we can make inferences. From the course of mathematical statistics, you are supposed to remember that there is a special statistic that is called t-statistic. And this t-statistic relates the mean, or like sample average, expected value of sample average, and sample variance, or the sample estimate of a variance, S squared. And this is the random variable. This is another random variable. So we believe that y bar is distributed normally. We believe that S squared is distributed based on the chi-square distribution. And the whole statistic has a student distribution. And for this student distribution, this is a parametric distribution. We know exactly the shape of this distribution, quantiles of this distribution. We are able to establish the probabilities regarding this distribution. So, by analogy, beta 1 hat has the same property. We can establish this t value for the beta 1 hat, and it looks like this. In the denominator, you have something that is called a standard error. So first of all, this is a t-statistic. It has a student distribution. And this SE beta 1 hat is called the standard error of beta 1 hat, and it is a sample estimate of this expression, square root of variance of beta 1 hat over n. So if you want to refresh your memory about sampling distributions, about the meaning of t-value and what is that, I can refer you to the lecture Sampling Distributions in Mathematical Statistics course. So now, going to the Python output. Standard errors, so the denominator of that t-statistic, are also reported in the regression output here. And we have them. And whenever we want to write the expression of the estimated regression line or sample regression line, we do like this. We have estimates, coefficient estimates here in usual place, and under these estimates we report, in parentheses, we report standard errors. So, with the knowledge on the sampling distribution of beta 1 hat and with the knowledge how to calculate t-statistic, we are able to do the procedure of single hypothesis testing. So, the idea of hypothesis testing is the following. Once again, we do not know the true value of beta 1, but we know something about the distributional properties of beta 1 hat, of its estimator. And if we believe, if we provide such conditions that beta 1 hat is unbiased and the expected value of beta 1 hat is beta 1, that I can simply plug inside this expectation in t-value the true population parameter beta 1. What it gives us? Suppose, related to the empirical example, that some skeptic suggests that reducing the number of students in a class has no effect on test scores. So what it suggests about the true value of beta 1? If there is no effect of x on y, we believe that beta 1 is 0. So this claim is a hypothesis, because we do not know anything about beta 1. We can hypothesize that beta 1 equals something. So the worst possible case for us is this: beta 1 is 0. It means that there is no effect. Why? It's a worst case because in this case we wanted to claim something that x affects y, and we found no relationship. So formally we write this as h0 is beta 1 equals 0. So this is called a null hypothesis. So we pose some claim, hypothesis, about the true value of beta 1, and based on our sample we want to test this claim to reach some tentative, careful conclusion whether it is correct or incorrect. Based on our sample estimates and based on t-value, we are able to test this hypothesis. So, the null hypothesis in most of the cases for single coefficients is such that this coefficient is 0. We have some special cases, but the special cases are going to be discussed later. So the usual case is beta 1 equals 0. What if we reject this null hypothesis? Then we have an alternative hypothesis. If H null is not true, then something is true. So we have 3 different types of alternative hypotheses. Right-sided, or also called upper tail alternative, that beta 1 is positive. Sometimes you want to know exactly that beta 1 is positive. Left-sided alternative, beta 1 is negative. Two-sided alternative, beta 1 is not 0. So we don't care whether it's positive or negative, we just want to know that this is not zero. So the two-sided alternative is used in most of the cases when we test single hypotheses about coefficients. So you need to state the significance level alpha for the hypothesis. Usually we take alpha as 5% or 0.05. So now you must find the rejection region for the corresponding alternative. So the rejection region depends on which alternative you have. For the upper tail alternative, T statistic from the previous slide, T statistics must exceed the 1 minus alpha quantile of a student distribution. So alpha is 5%, then it's 95% quantile. For the lower tail alternative, T must be less than minus 95 quantile of a student distribution, and for the two-tail alternative, the absolute value of T must exceed T 1 minus alpha over 2 quantile. So it means that now it's going to be 97.5 quantile of a student distribution. So as I said, this expression means 1 minus alpha quantile of a student's distribution with n minus 1 degrees of freedom. So don't forget that student's distribution has another parameter, which is n, which is degrees of freedom, usually n minus 1. So here's an illustration of a rejection region. For the right tail alternative, the rejection and 28 degrees of freedom, the 95% quantile is equal 1.701, and if T statistic falls into this right-sided rejection region, then we reject null hypothesis in favor of an alternative that beta 1 is greater than 0. So for 18 degrees of freedom and for the left-sided alternative, 5% rejection region is on the left tail of the student's distribution, and the quantile is minus 1.734. And any t value that belongs to the left interval rejects a null hypothesis and in favor of an alternative, left-sided alternative. Now, if you have 25 degrees of freedom, 5% level of significance, then rejection region consists of two parts. One to the right of 2.06, which is 2.5%, and one to the left of minus 2.06. So as I said, usually we are interested in the null hypothesis that beta 1 equals 0, which means that x does not have an effect on y. So well, if beta 1 is 0, then t value looks like this, or it's simply beta 1 hat divided by the standard error. The most common level of significance is alpha equals 5%. For large samples, greater than 100, the quantiles of students' distribution approximately equal to quantiles of a standard normal distribution that we denote with z, 1 minus alpha. That's why in the Python output you have z instead of t. And there are two most popular values for these z quantiles. For 95% it's 164, for 97.5% it's 196. So those are the most useful quantiles. And if we want to test the null hypothesis versus the two-sided alternative at 5% level of significance, then we must ensure that the absolute value of t, beta 1 hat over standard error of beta 1, is greater than 196. In this case, we reject the null hypothesis at 5% level of significance, and we are sure that beta 1 is not equal to 0. When beta 1 is not equal to 0, x has an effect on y with alpha level of significance. So these t values are already calculated for you. As I said, in Python, they're called z, and they are here. Basically, you divide coefficient by the standard error, and you have these. You divide this coefficient by standard error, and you have these. Whenever you have the reported values of coefficient and standard error, you are able to calculate t values yourself. In our case, we have -4, there is a typo, -4.399, and at the absolute value exceeds 196, and this means that we can reject the null hypothesis that beta 1 is 0 at 5% level of significance, that the class size doesn't have an effect on test score. So we're definitely sure that the class size has a negative effect on the test score based on this hypothesis test. Alternatively, we can use p-value instead of t-value, and this is even simpler. So p-value is the smallest level of significance for which the observed data indicates that the null hypothesis must be rejected. So the smaller p-value is, the better for us, because it must be less than alpha. It must be less than 5%. In order to reject null hypothesis, p-value must be smaller than alpha. And here we have an illustration. So if we have 40 degrees of freedom, and if t-value is 185, it means that 185 and minus 185 separates the area to the left and to the right of 0.0359, and the same here. So together it is something like 7.18%, and 7.18% is greater than 5%, so we cannot reject the null hypothesis at 5% level of significance in this case. So in our case, in the regression output from Python, we have these p-values, and you see that they are less than even 1/1000th of, like it's less than 0.1%. Which means that p-values are less than 1%, and we can reject the null hypothesis even at 1% level of significance. So the class size definitely has an effect on the educational output, on the test score. And there is a strong, significant statistical relationship between these two values. And we can claim this based on the p-values. And the next object of a hypothesis testing that leads you to the same conclusion is the confidence interval. So the confidence interval is a rule to calculate two numbers that form the endpoints of the interval that is intended to enclose the population parameter of interest. So confidence interval and both boundaries of this interval are random variables. Depending on your random sample, confidence interval will be different. And with the given probability, which we call confidence level, this confidence interval would enclose the true population parameter. So if beta 1 equals 0 falls into the confidence interval, we cannot reject the null hypothesis. Why? Because the confidence interval tells what are the values of population parameter with a given level of confidence. So here in the regression output, we have also the report on the 5% on 95% confidence intervals for the intercept and for the slope. So this is the left or lower confidence limit. This is the upper confidence limit, left and right confidence limit. And we see that 0 does not fall into this interval for the slope. And with 95% probability, we can tell that beta 1 is between these two numbers. So, sorry, once again, there is a typo here. It must be -3296. So the 0 does not belong to this confidence interval, so therefore we can reject the null hypothesis that the class size has an effect on test scores. So once again, here we must have this number, -3296. So now, what if we have a binary variable as a regressor? A variable that takes only two values, 0 or 1. This is very common practice in econometrics to use binary variables as regressors, and we will have a lot of them during the course of Econometrics II. So another names of a binary variable are indicator variable or a dummy variable. So suppose we have the following model: y equals beta 1 plus beta 0 plus beta 1, d plus u, and d equals to 0 or 1. So those are two possible values of this dummy or indicator variable. This is very simple. When d is 0, then conditional expectation of y is just beta 0. When d is 1, you plug 1 here, and the conditional expectation of y is beta 0 plus beta 1. So the meaning of beta 1 now is different. It's not a slope because there is no line. Now, this is the difference between the conditional expectation of y when d is 1 and when d is 0. So this is a difference between two populations. Let's say one population has d equals 0, another population has d equals 1. And beta 1 is the difference between these two populations. In our example, let's define the binary variable in the following way. Let's say, well, if the district falls into the district with small class sizes, and such district would have d equals 0 only when student-teacher ratio is less than 20. Or we call this district with the large classes, d equals 1, when student-teacher ratio is greater than or equal to 20. So this is a new variable for us, depending on the value of STR, of student-teacher ratio. So this is the model, population model. And now when we estimate our model, we will have the following outcome here. So you see that both values are statistically significant. It's easily visible when you divide coefficient by standard error. If it's greater than 2, then you are fine and both estimates are significant. And in the case of this regression, what do we have? So 657.35 is the expected value of a test score in districts with student-teacher ratio less than 20, with small classes. And if d equals 1, then 657.35 minus 737 gives us slightly lower number, 649.98, which is the expected value of a test score in districts with large classes, where student-teacher ratio is greater than 20. And minus 7.37 is the average difference in test scores between classes with high and low student-teacher ratio. In Python, you will get this output. So these are coefficient estimates, and these are p-values based on which you can consider that both estimates are statistically significant, and null hypothesis that true betas are 0 can be rejected. So now let's discuss what happens if the main assumption of OLS estimation does not hold. So if the other factors contained in UI that are supposed to be unrelated to X actually are related. So you cannot formally test this assumption. You always need to reasonably think if there is a possibility that something else affects Y and is connected to X simultaneously. So based on this assumption, we prove that beta 1 hat is an unbiased estimator, which is a desired feature of this estimator. But if this expectation is not 0, and there is another variable x2 that influences Y and is related to x1, what happens? In this case, the expectation of beta 1 hat is going to be biased. It's not just beta 1, it's gonna have this additional term. And this additional term is called omitted variable bias. And it doesn't matter whether you have large sample or small sample, it is still biased and your estimation of beta 1 is going to be incorrect. So in the lecture Multiple Regression in Econometrics, you have the derivation and proof of this formula and why the omitted variable bias looks like this. So the bias consists of two terms. So this is a product of beta 2, and beta 2 is the coefficient how x2 affects y. So if beta 2 is not 0 and x2 is the determinant of y, then we have this term here. And the most important, so there, as you remember, there are many factors, other factors in the error term that may potentially affect y, but if they are not related to x1, then we are safe. But if x2 is correlated with x1, if the covariance between x2 and x1 is non-zero, then this bias appears, and beta 1 hat is a biased estimate. So from the bias formula we can infer the direction of bias, whether it's positive bias or negative bias. It is very simple. If you know how to multiply two numbers, you know that if beta 2 is positive and covariance is also positive, then we have a positive bias. If covariance is negative, we have negative bias, and the opposite for beta 2, negative. If x2 negatively affects y and covariance between x1 and x2 is positive, then we have negative bias. Otherwise, it's going to be positive. So, for our example on the test scores, suppose that there is another variable, which is a percentage of non-native English-speaking students. Why this variable can lead to the omitted variable bias? First of all, English language ability may affect the test scores, and you probably understand this because English language is not your mother tongue, it's not your native language, and probably you have some difficulties with the understanding of the material. And if we have schools where a lot of non-native English speaking students learn, then probably it may affect the test scores in that district. So x2 is a determinant of y, so the first condition holds. Now the second condition is the percentage of non-native English speakers related to the class size. And the reasonable suggestion is yes, because immigrant communities tend to have smaller school budgets, so kind of immigrants live in the poor districts. So those poor districts have less money, and less money means that teachers must work with many more students. So x2 is correlated with x1. Now let's think about if this percentage is high, then beta 2 is potentially negative because high number of non-native English students would affect negatively test scores. What is the correlation between STR and the percentage of non-native English speaking students? It's potentially positive. The more immigrants you have, the higher students-teacher ratio. So the direction of bias in this case must be negative, right? So there must be true beta 1 minus something, minus this negative bias. So let's see if it's true or not. So let's analyze two additional variables before we see whether beta 1 was biased or not. Time of the day of the test. Well, maybe you can feel you can feel tired if the test happens in the second part of the day, or maybe you are sleepy if the test holds in the first part of the day. So the time of day could affect test scores. But is this related to the student-teacher ratio? No, there is no reasonable idea how the time of day of the test may be connected to the student-teacher ratio. So there is no bias because the second term is 0. Parking lot space per student. Well, parking lot space does not affect an educational outcome. So learning takes place in the classroom, but not in the parking space. So therefore, test scores are not affected. Beta 2 is 0, but there is a correlation between parking lot space and student-teacher ratio, because if the school is rich, then probably you have more parking places and more teachers and less student-teacher ratio. So no bias in this case. So we have only one potential problem here with this percentage of non-native English-speaking students. So how we can overcome omitted variable bias? So the first thing is to run a randomized control experiment. So randomly assign treatment, so student-teacher ratio between districts, and then look at the educational outcome after some time. It's not possible. It's not realistic. We cannot make experiments over people, over students. It is completely unrealistic. What we can do? We can include omitted variable, percentage of English learners, into the regression. And in this case, we will get a multiple regression model. So now instead of one variable, str, we have two variables, str and pctel. And with the help of this inclusion, we can potentially control for the biased estimate of beta 1. This is called a multiple regression model, and the outcome of the estimation procedure is in front of you. So now we have a coefficient of student-teacher ratio, which is much, so the effect is weaker. It's closer to 0 now. It was -228, now it's -1.5. 0.1, which means that exactly negative bias led to this estimate of minus 228. All coefficients are statistically significant, so we reject null hypothesis for each of them. And so here is a comparison of these two models. So that was the single regressor model. Now we have the multiple regression model, and you see that coefficient in the absolute terms reduced, in normal sense increased, right, from minus 228 to minus 1.1. So now student-teacher ratio has a smaller impact on the test score, controlling for the percentage of English learners. So we reject the single null hypothesis that beta 1 equals 0, beta 2 equals 0, so both are significant. And the coefficient falls by 1/2. This is exactly the effect of omitted variable bias that was here in the first model. So holding percent of English learners constant, districts is one more student per teacher on average have test scores that are 1.1 points lower. So now the effect is weaker. Holding students teacher ratio constant, districts with 1 more percent of English learners. If you have more non-native English speaking students, then you will have the test score on average 0.65 points lower. If we add one more variable, expenditures per student, which is also reasonable, the more money a school spends on students, the more potentially the richer is the school, so probably the school can attract better teachers and the educational outcomes are going to be better. But now look what happens. Now in the model, we have almost close to 0 coefficient on student-teacher ratio. Nothing has changed with the percentage of English learners. There was minus 0.65, now it's minus 0.66. Nothing. One additional thing which is interesting, this coefficient is not significant anymore. Look, we cannot reject the null hypothesis that beta 1 is 0 because p-value is greater than 0.05, and we see that t-value now is even less than 1/2. And we want it to be greater than 2. So what happens? Does this mean the student-teacher ratio does not have effect on test scores after we control for the expenditures of a school? And look, let's think about the relationship between STR and expenditures. If a school has more teachers, this school spends more money because teachers must be paid salary. And in this case, we definitely see that STR and expenditures are correlated. They are closely related to each other. And this is called a problem of multicollinearity. You don't want two variables that are close to each other to appear together in the same model. You need to choose only one of them, because now we see that the effect of student-teacher ratio is fully absorbed by expenditures. The more expenditures the school has, the less is going to be student-teacher ratio, because you will have more teachers, definitely. So we should leave one of these two variables, either STR or expenditures, to avoid the problem of multicollinearity. Now, what if you want to ask whether both STR and expenditures do not have effect on test score together? We need to make a procedure that is called multiple hypothesis testing. Now the null hypothesis is beta 1 equals 0 and beta 3 equals 0. So this and is crucial here. So both coefficients simultaneously must be 0. The alternative hypothesis is that one of them is not 0, rather either beta 1 or beta 3 or both. How should we test the joint hypothesis? For the joint hypothesis, we use a different statistic. And this different statistic is called F statistic. And here we have an output of the Python calculation, and F statistic, F value is here, 5.48597. And we have p-value. So based on the p-value, we are able to either reject null hypothesis or not reject null hypothesis. So since p-value is very small, it's less than 1%, we reject the joint null hypothesis, and either STR or expenditures have effect on test score, or both of them. But they are not both 0. So remember that whenever we want to test simultaneous effect of 2 or more variables, we are not able to use T statistics. Now we need to use F statistic, which is calculated in its own way. If you want to know how F statistic is calculated, so please go to the lecture on multiple regression models in Econometrics. We had the proper formula for the calculation of F statistic. So the last part of this lecture is devoted to the nonlinear regression functions. So before that, we spoke about the linear relationship between x and y. Now, let's see the example. Assume that we want to know how test scores depend on district income. If richer districts have better educational outcomes, if poorer districts have worse educational outcomes. Let's see. So here we have the scatter plot, the data points for districts where on x-axis we have district income and on y-axis we have a test score. And look, if I put here the linear relationship and straight line, then this straight line poorly fits the data. But if I try to draw here a curve, so this curve fits data better. This is an idea of a nonlinear specification, nonlinear regression. We want to have a nonlinear relationship between district income and test score. And there are different ways how we can do that. The first way is called a polynomial specification. So obviously the right picture demonstrates the better fit of a regression line. So there are different nonlinear functions that you know from the school, from mathematics, and so one of them is the polynomial. So we can write down the following relationship between income and test score. Together with the income, we have the second order of income squared. Look, formally, we have something similar to the multivariable model from the previous part of the lecture. So we have one variable here, another variable here, and we are able to estimate beta 0, beta 1, and beta 2 using ordinary least squares estimators. The only thing here that we need to create a new variable income squared. And now the effect of this variable changes because the effect of income on test score is no more linear. And whenever we take the partial derivative of test score with respect to income, we have beta 1 plus 2 beta 2 times income. So the effect of income depends on the size of income. And you see this for the poor districts. Increase in income has a strong impact on the test score. So the test scores improve very fast. But whenever the district income reaches some high levels, the increase in test scores slows down. And actually it reaches some maximum around $40,000. It's visible here on that picture. So this is exactly this non-linear effect of test scores, of income on the test score. So here is the regression output. The coefficients of on the income, on income squared, all coefficients are statistically significant. We strongly reject null hypothesis for each single coefficient. And the estimated model looks like this. The test score is negatively related to income. Basically, the first order has a negative coefficient estimate, and the second order also has a negative coefficient estimate. When we take the derivative of a test score with respect to income, we have this expression. So 385 comes from this, and this coefficient minus 0.0846 comes, this is 2 multiplied by beta 2. And the higher the income is, the less the impact of income on the test score. So let's see how it works. So the marginal effect of income on test score is diminishing. When income gets higher, the effect becomes weaker. So for example, if income changes from $10,000 to $11,000, the test score changes by 296 on average. So you simply plug 10 into the model, you calculate what is the test score if it's 10, then you plug 11 into the model on place of income, income squared, calculate test score, calculate the difference, and you have this 296. Whenever income changes from 40 to 41, and I do the same procedure, I take 40, plug into this formula, income here, and I get some test score. Then I plug 41, do the same, and the difference is 0.42. So you see that the same improvement in income by 1 unit has the less impact when income is high. And we see this from the marginal effect here, because whenever income increases, the whole marginal effect decreases. So another form of nonlinear function is the logarithmic specification. And there are 3 possible cases of logarithms in regressions. So one case is the so-called linear log model. So y is in levels, x is in logarithms. So we are taking the logarithm of x and we use this as a regressor. So the interpretation of beta 1 in this case is the following. If x changes by 1%, y changes by beta 1 divided by 100. Another logarithmic specification is the log linear, very popular specification when you take the log of y, but x is given in levels. So now the interpretation of beta 1 is different, because a change in x by 1 unit is associated with 100 times beta 1% change in y. So look, this is very simple. When you see the logarithm, then this variable changes by in percent. Either x changes by some percent or y changes by some percent. Another variable, which is in levels, changes by units, but whenever you are using change in percent, you need to divide beta 1 by 100. Whenever x changes by units, you need to multiply beta 1 by 100. And log-log specification, when you have both logarithm in y and in x. So now a 1% change in x is associated with 1% change in, beta 1% change in y. And beta 1 is called the elasticity coefficient of y with respect to x. So now let's see how these logarithmic specifications are related to our problem. So linear log regression. So log is in district income and test score is in levels. You see that this specification looks very similar to the polynomial of order 2. So when we have a log linear regression, so now look in the on the vertical axis we have the log of test score, and we have linear relationship between district income and test score here, which does not fit very much. And for log-log regression, we have also this curve, which fits the data very nice. So both linear log regression and log-log regression are appropriate to model this relationship between district income and the test score. So now let's see on the estimates. Here, linear log model. What is the interpretation of 3642 once again? If income changes by 1%, test score changes by 0.3642 points. So you need to divide this coefficient by 100. So this one, if income changes by $1,000, so by 1, then the test score changes by 0.28%. Why I need to take this coefficient, multiply by 100. If I have log-log specification, when income changes by 1%, test score changes by 0.0554%. And what do we have? This estimate is significant, this estimate is also significant, and this one is also significant. So all three models have statistically significant coefficient estimates, but considering the better data fit, so the first model and the third model are better to describe the data. So the last case of nonlinear specification is the interaction between binary variables. So between variables. So we start with the binary variables. So consider the question, what if the effect of one variable depends on the level of other variable? For example, smaller classes have stronger effect on test scores in districts where are many non-native students, and weaker effect in the other districts. So remember that idea that non-native English speakers usually have or expected to have lower test scores. So now let's assume, so probably it is possible that for those districts, decrease in the student-teacher ratio have a stronger effect than the same reduction of STR in the districts where not much of the immigrants. Sounds reasonable. How we can model this dependency of one variable on the level of the other variable? So we want to model the situation when the partial effect of x1 on y depends on x2. So we model this with the help of something that is called interaction term. So this is the model. We have one binary variable, another binary variable, and here we have their interaction. So the product of D1 and D2. And this term is called an interaction term. So if D2 is 0, put 0 here, put 0 here. So what do we have? We have this expression, y equals beta 0 plus beta 1 d1. So change in d1 affects y by beta 1. If d1 changes from 0 to 1, y changes by beta 1. You should remember this from that previous discussion on the binary regressors. If d2 equals 1, then this is 1 and this is 1. And whenever d1 changes from 0 to 1, so b1 and b3 now turn on. So it means that y is affected by beta 1 and beta 3 together. So that's exactly what we want. The effect of d1 depends on the level of d2. Let's see how it works in the example. So let's define two binary variables. So one binary variable is the familiar variable that we already used in this example. So it's high str, 0 when student-teacher ratio is less than 20, and 1 if the student-teacher ratio is greater than or equal to 20. And another binary variable is high EL, which means that we have 0 if in the district there are less than 10% of non-English speaking students or English learners, and 1 if this percentage is greater than or equal to 10. So here is the estimation output. The test score equals to this formula. And then let's try to understand what is the meaning. So for districts where the percentage of immigrant students is less than 10%, so there are not much of immigrant students, the change in the student-teacher ratio affects the test score by 191 with minus. So kind of increase in the class size from small class to large class decreases the score by 191. Now, for districts with the large immigrant society, for a lot of immigrant students, this high L equals 1 here and here, and now when we switch high STR from 0 to 1, the effect is minus 5.4. So the effect is stronger. Whenever class size is increased, in immigrant communities, the reduction in test score is more pronounced. And we see this from the numbers. But the problem is that the interaction term is not statistically significant. So we cannot tell that this interaction term matters, and basically this effect is different in districts with large and small immigrant community. Here, the value is greater than 5%. So we cannot reject the hypothesis that the true coefficient here is 0. So now we can do the interaction between binary and continuous variable. So suppose instead of high or low student-teacher ratio, we want to use the usual variable, continuous variable of a student-teacher ratio. That's going to be x, and d would represent this binary variable. Either we have a lot of immigrant students or the small share of them. And then the slope of a regression line can depend on the level of d, on the binary variable. So basically there are three possibilities. So different intercepts, same slope when we just introduce this binary variable as an additional regressor. So you see that when this regressor turns in, we have beta 0 plus beta 2 as the intercept. Different intercept and slope when we introduce exactly this interaction term, that's what we want. And the third possibility, same intercept, different slope. We don't introduce this binary variable separately. We introduce this only in the interaction term. And here is an illustration. So the first case is represented here. Look, depending on the level of D, either it's 0 or 1, we have either this line starting from beta 0 or this line, beta 0 plus beta 2. But their slope is the same. So the effect of X is the same for both groups, for both populations. Now, for the second case, that's exactly what we want. This is something like a flexibility for us, because we have different intercepts and different slopes. For this group, the effect is weaker. For this group, where D1 is 1, the effect is stronger, right? So the slope is steeper. And the third case is somewhat redundant. They start from the same intercept, but they have different slopes. So usually we go for the second model. So we have this binary variable, high EL, and if we introduce this as an interaction term with str, we have this. So what it means, let's see. When the district does not have too much of immigrants, then the tests, then the sample regression line looks like this, and one additional student in the class decreases the test score by 0.97 here. When we have schools with the large immigrant community, more than 10% non-native students, then slope is different, 225. So one additional student in such districts reduces the test score by 225, which is a stronger effect. Once again, the problem is that the interaction term is not significant, and we cannot prove that, or we cannot reject the hypothesis that both slopes are equal because of this. We cannot claim that there is a different effect between these two districts. The slope of two lines is the same. And here is the regression output, where we can see that the interaction term is not statistically significant, and basically this dummy variable is also not statistically significant separately, 0.772 here. So this was the last slide. Now, after watching this video, you can find the assignment where, so this assignment consists of 10 questions on the material of this lecture. So please be short and precise answering all those questions, because the most important thing when answering these questions is such that you need to show that you understand this material. No need to write a lot of words if they are meaningful. Better to write several sentences, but these sentences should be precise, and they should demonstrate your understanding of the material. Good luck with this.